Hello, friends. Welcome to the ATC Double Cut. I am pleased to welcome Dr. Bill Kreuser, the president of the Greenkeeper app, to the show. Welcome, Bill.
Hey, Micah, how you doing?
I'm doing good. I remembered you're not just the president of the Greenkeeper app. You have been the golf course superintendent at the Jim Egger golf course in Lincoln, Nebraska.
Yeah, we've been working out there, handling some of the day-to-day and planning the agronomics, and it's been a great opportunity for me to bring some of the theories, concepts, and ideas that we've had for, a couple decades to the real world and see how to actually get them to work in practice.
That's pretty cool. I was talking with Dr. Bob Wolverton a couple of weeks ago. We were at the Australian Open, and he's one of those rare PhD golf course superintendents. There's Dr. Brett Morris in Australia, who's with Syngenta now, but he was a golf course superintendent for a while with a PhD. And there's John Dempsey in Ireland, who had a PhD while he was a superintendent for a while. But there's not a lot of PhDs who are full-time superintendents. So I was talking with Bob saying, yeah, I think you're one of the only ones in the world, maybe the only one I can think of. And I forgot about you. So let's give you credit for that.
Yeah.
Yeah, I contacted you last week and I said, let's talk as soon as possible because I got in my email the monthly Greenkeeper app or Greenkeeper newsletter. It seems to come monthly. How do people sign up for that if they don't get it?
Yeah, I wish it was more frequent. You can just register for a Greenkeeper account. It's free. You'll have a 7-day trial, but in doing so, you get onto our email list. And so just by signing up with your name and email, even if you don't even connect to an actual golf course, you will then be on the list. Same thing if you take a Greenkeeper university classes. Same thing, you get into our user database and then we send it out. So it goes out to about 9,000 people. Okay. I wish it was every 2 weeks, but I've been a slacker. I'm not as good as you about getting content written. Even that last post, it took me like 10 hours to write. It's like 1,700 words. And it was just like, I got so much going on, but I felt like I needed to give it some good description since it was a new concept for us.
Right. So this is the post that we're talking about, which is like a blog post, and it is on the blog, and so you can see it on the Greenkeeper website. It's about a brand new model that I know you've been working on this for a long time, and I was so excited to read about it. It's a new model, not for growth regulators, which everybody, thinks of you as the PGR guy, but this is for another product that almost every turf manager around the world growing turf on a sand-based root zone uses, and that is soil surfactants, or as they're commonly called, wetting agents. And I was like, wow, this is awesome. And I read the post and I'm like, wow, this is really cool. I want to talk with Bill immediately. And then we couldn't quite get it set up until now. So we're talking about it, and I've had a chance to read that post twice now. So thank you for writing such a nice post.
Well, thank you, Micah. No, it has been something we've worked on for a while. And yeah, I've done a lot of modeling of plant growth regulators. But really, I feel like one of my biggest pet peeves of everything is just inefficiency. And I think when it came to scheduling PGRs back in the early 2000s, and I had that backyard putting green, and it was just, everybody was giving me different protocols and ways to apply the materials, and there wasn't a clear way to just efficiently apply these products. And I think the same thing is really common with wetting agents, and you put down wetting agents, and some people do it weekly, some people do it every month, pretty commonly. And then there's people that try to stretch it out with a couple heavy applications in the spring and then go 90 days throughout the summer with those materials. And it just was confusing to me that there could be so many different programs out there. And so since 2017, when I was still at the University of Nebraska, We got a grant from GCSAA to try a method to measure wetting agents in like leachate of water to kind of quantify them. And that didn't work. And we tried all these different methods. And then finally, in the last 2.5 years, we came up with a nice way to try to characterize, is a wetting agent working or not working, so that we can give end users some perspective as to when they need to schedule applications.
Very, very good. I think if we have time, we're going to talk through this in all kinds of detail. So we'll talk about what method that is that you came up with to kind of figure out how to check if a wetting agent is working or not, and how to model that. And then we'll talk about what the implications of that are in terms of what, like practically how many days that is, or how many growing degree days that is. But I seem to recall that you were working on this or thinking about it even sooner. Wasn't Glenn O'Bear working on this a little bit? Because I thought I talked with him in 2016 about this.
We were starting to have those discussions about, how does everybody apply differently? There's a really phenomenal superintendent in Nebraska. His name is Josh Mahar. He's at Wild Horse Golf Club, top 100 course, really amazing putting greens. And, he told me that wetting agents, you just need to get them out every 2 weeks. And that was really the impetus that Glenn and I starting to talk when he was working on his PhD with me was, how does everybody have such different schedules? And how do we try to understand what's working or not working? And the biggest challenge with the wetting agents are there's so much variability in the labels and the materials, and there's a lot of secrecy because they're not products that are registered with the EPA like a pesticide. So you just are incredibly reliant on marketing language. And then you wonder, well, where did they get their data? How did they evaluate when things needed to be reapplied? And they had all kinds of different ways of doing it, like measuring with moisture meters and trying to get an idea from that. And I'm not really a huge fan. I mean, that's great for comparing maybe one wetting agent to another at a specific day, but the numbers aren't something that you can use to understand, is the wetting agent doing anything or not relative to when we just applied it. So then we started trying some more advanced methods. Glenn left and took a job at X-Acto and worked remotely on his PhD on iron layer formation and putting greens. We had some other students try to do some things with different equipment, and it just wasn't working out the way that we wanted. You may even remember I tweeted out we were growing pots, like about half a meter diameter pots, full USGA putting greens, and we were measuring leachate, and we had moisture meters at different depths installed horizontally, and we even had a reel mower that you could pull along that was powered by a drill to mow the plots at fairway height. And they looked cool. A lot of people saw it on social media, but it still wasn't getting us what we needed to. And so that's to figure this out. And so that's just what it is. It's a science. You're constantly iterating. You're constantly pulling in information from other people, from other researchers. And you just try and spend a lot of money, unfortunately, failing. And eventually you figure out how to make it work.
Mm-hmm. Yep, that's how it goes. Well, Bill, with this being the ATC double cut, I'm going to go ahead and introduce a blog post on the ATC website that kind of serves as a starting point of the discussion. And then we're going to go look at that blog post that you put up. But I'm going to show on my screen. I don't think you'll be able to see it. Well, I know you can't, but you'll see it later if you watch the video recording of this. I'm showing a post that's on the ATC website with the title, "What do wetting agents really do?" ? And that's a post that I wrote many years ago after I saw a nice article, a summary article by Karcher and Richardson that has one of those amazing photos that they show of the hydrophobicity and the localized dry spot that develops on their bent grass green in Fayetteville, Arkansas. When they don't apply wetting agents compared to the plots that do have wetting agents. So I think you may have seen that type of picture where they have such a stark difference between those. Anyway, I start off in that post by saying, I quote from their article. This is by Doug Karcher and Mike Richardson. It's an article that they wrote some years ago, and the quote is from them: "It is often stated that some wetting agents move water rapidly through the root zone, while other products retain considerable moisture near the surface, but the data to substantiate such claims is limited." And I then went on and discussed more about their research, and I ended with a quote from a 2010 article by Soldat and Cousseau and Lowry. And that was their 2010 soil science article, which for me, it was back then that I started. I mean, I thought that article that Doug wrote in soil science back in 2010 really made things clear for me. And you may recall or be familiar with that research. I know that Doug is.
I ran the research for Doug. Yeah, we collected the data with my best friend.
Okay.
So, yeah.
Okay. So this may be familiar for you. I don't think that I pulled this quote from the abstract. I'm pretty sure it was right near the end of the article, and it said highlighted. The quote is, "The surfactants had a minimal effect on soil water content. However, the 3 surfactants significantly improved soil moisture uniformity compared with the untreated control in both years during drought conditions." So anyway, I'm going to recommend my blog post about what do wetting agents really do as a way to answer that question and get links to some really interesting research. Let's now transition to your blog post, which has a title, "A New Era in Wetting Agent Programming." And I've brought that up on my screen now, so anybody who's watching the video of this will be able to see it. Let's just talk a little bit about what is this new era. So I've given a little bit of a background of what wetting agents really do and what they do. I mean, if I explain it, and I haven't done research on it, I've just read research, but I think that I can explain it, what they really do, pretty simply, which is they improve the uniformity of soil water content. So they make the water distribution in the soil more consistent from location to location, and they help to prevent hydrophobic conditions, and they make it easier. If you have applied a wetting agent, they tend to make it easier to re-wet the soil after it dries. So I think that's my one paragraph summary of it. Can you correct me?
No, that's exactly it. And again, there's so many parallels to the PGR research where the growth regulators, we had 2 decades of study talking about how they reduce POA and they increase color. And there's all these kind of, I call them secondary benefits. And the primary benefit of these materials were to suppress growth rates. And then you would see these secondary benefits manifest later. Well, I think the same thing with the wetting agents. The wetting agents primarily are helping water infiltrate a soil, especially as it starts to become a little bit hydrophobic or resistant to water infiltration, and then make sure that that water is more uniformly distributed through that profile. And then when the wetting agent's there, that time is reduced. You see less variability, which then results in less localized dry spot and being able to bring the water contents to lower levels without seeing wilt starting to show up in different pockets. So those are kind of the secondary things you might measure with a TDR probe or a drone shot to see the spots heating up. And so I really wanted to focus on what is the wetting agent doing? It's helping water get into the soil. Then you think, what test can I do to evaluate that? And it's the most tedious, boring of all the tests you can possibly do. But essentially, we just take little cores out of the putting greens, let them dry for at least 2 weeks. So they're completely dried out, just air dry though, and warm 80-degree type room. And then you just put a 1 milliliter drop of water in, and you just time it. And when does it infiltrate into that core completely? A wettable sand will go in seconds. A non-wettable hydrophobic sand can take 10 minutes or more. And so that was the metric. We had something to evaluate. And so that's been around for a long time. But one of the things we wanted to do differently was look at what is the variability of those infiltration times and sands that are not treated with a wetting agent versus to sands that are just treated like the day before. So it's similar to the growth regulator parallel again. What's the growth rate of a grass that's not treated compared to the growth rate of the grass that is just treated with the PGR, and then monitor that over a time course. So we took the same approach with the wetting agents, where we applied the wetting agent and then we just frequently sampled and started to see when does the variability in the infiltration time start to really spike, and also when do we see that the average time for water infiltration starts to go to what it was before a wetting agent was applied. So we were able to use that as a metric, both the variability and the infiltration time average, to compare the before and the after of a wetting agent application. And so that was the method, that was the system that we could use.
Perfect. Let's talk about that a little bit more, because when I was reading it, and then when I read it again, it seemed to me that it made perfect sense. But I'm afraid that as we have this discussion, that if people are hearing this for the first time, it may be a lot to comprehend about exactly what the test was and why it's meaningful, and then how you actually had plots on the green that were treated and not treated, where those cores came from, and that this was on a real golf course, in-play golf course, and what grass types it was and stuff. So let's just talk about all those details as much as we can, because I imagine anybody who's watching or listening to this probably cares about all of these details and will be interested in this stuff. So
perfect.
This technically, like, just for consistency, this is called the water droplet penetration test. Is that right? Is that the technical word?
Yep, that's what it is. And then it gets a little confusing because we talk about penetration times, which is the result of the test. So it's like a stimp meter is measuring ball roll or green speed, and then feet is actually how far the ball rolled. So the time is the metric here that we're measuring. And so that's a little bit of how that works. And I guess the thing we want to, let's just go ahead.
No, you go.
Okay. I think, let's just talk a little bit about what does the variability look like in a putting green first. So this research was done on a 9-hole par 3 golf course in Lincoln, Nebraska. 70-year-old putting greens, largely just push-up greens, but we, in the last 6-7 years, have introduced 4 inches of sand cap on top of decades of light top dressing. But there's definitely layers. And so we have a situation where we have very typical natural levels of hydrophobicity in this sandy organic matter layered system. And so if I took cores from that, let's just use some round numbers. If I took some cores, say I took 10 cores out from randomly around that green and dried them, and then 2 weeks later put a drop of water 1 inch below the surface on the side of the core. So you lay the core on its side, let it dry, put a drop of water in, and time it. And we did it at about a little under 1 inch, about 2 centimeters. So we put that water there. You would see the average of those 10 would be a 10 cores might be 20 seconds for the water to infiltrate. Okay. And it does change from day to day. So let's just say this is kind of an average, just a thought experiment type of a thing. So you put in the drop, it takes 20 seconds on average. Some of those cores, though, might be 5 or 10 seconds to infiltrate. Other cores could easily be 30 seconds or as long as 10 minutes. Okay. But the average, the mean and then where the median is closer to 20-second infiltration time. If I put a wetting agent like Counteract Firm down, what I find is that the infiltration time now, instead of being 20 seconds with about plus or minus 10 seconds of variability, the next day after I water it in, take those cores, dry it, go make the measurement, it's now 10 seconds to infiltrate plus or minus 5 seconds. So not only is the infiltration time went from 20 seconds on average to 10, the variability also got halved. So now it's maybe as long as 5 to 15 seconds infiltration instead of 5 to 30 seconds of infiltration time without the wetting agent. And so then we're just going to keep sampling to figure out how much time did it take for that variability to spike again and to see those infiltration times return to what they were pre-wetting agent application.
Thank you. And you answered one of my questions that I had, because I did not read it in the blog post, and that was what depth in the soil. And I don't know if the water droplet penetration test is is the standard to be 2 centimeters below the surface, or that's just what you picked for the depth.
Traditionally, you would do it at different depths.
Mm-hmm.
So you would go, I think, on 1 centimeter spacing, from 1 all the way down to 5, 6, 7 centimeters, depending on how long. For this, we just wanted to simplify the method. And so we just thought, essentially a lot of hydrophobicity is happening near the surface. I didn't want to have it right at the surface because of things like disruption and top dressing that would maybe affect it. So around the 2 centimeter depth, we thought was a representative spot to do these tests, knowing that it might be different levels, but at least we can verify too. If you put the wetting agent in and I watered for 8 or 10 minutes, which is about 1/10 of an inch of water, and then water heavy the following night, I should definitely be getting the wetting agent to that level. So it should be having an effect there.
Mm-hmm. Yeah. I'm reading in the blog post, and I recommend everybody go to the greenkeeperapp.com website and check out their blog section up at the top, and then you can get the most recent post, which is a new era in wetting agent programming, and you can get all these details, like seeing that it was watered in for 8 minutes. And you said that's about 1/10 of an inch of irrigation?
Yeah, it's a little more. It depends on the green, right? We've done catch cans. Some areas that's a lot more. Some areas it's not as much. It's real world. It's just square irrigation, infinity heads, like 60 yard spacing. So, or 60 foot spacing, I guess. So it's somewhere around 1/10 to 1/1500th of an inch is kind of the average.
And the water droplet penetration test, it's really cool. If anybody hasn't done it, I recommend doing it just to assess the tendency towards hydrophobicity of the soils that you're working with. It's really interesting how a sand root zone tends to become so hydrophobic as it dries. So what you described, you're taking the cores, you're letting it dry for 2 weeks or longer. It's just air drying, but that in a sand root zone, that gets it completely dry. And sands tend to get extremely hydrophobic. Well, I mean, I don't know if extremely is the right word, but they do tend to sometimes get to the point where you put a drop of water on it and it just won't go in. It just sits there. And so it becomes easy to time it, because if it's not hydrophobic, the water goes in real quick. And otherwise it just sits there. It just sits there, and it sits there for a long, long time. In fact, I remember that there's a post or a video, maybe both, on the Pace Turf website. I'm going to put a link to those also in the show notes. I'll put a link to this post from the Greenkeeper app, obviously put a post to the one that I give the double cut treatment, the what do wetting agents really do, and also a couple from Pace Turf, because Pace Turf had a guideline of like you really need to apply a wetting agent if your water droplet penetration test is beyond a certain number of seconds. And I forget exactly what threshold they were using, but I'm going to look that up and share that also. But anyway, if you haven't done this before, you might not realize how effective just simply taking a core and air drying it is to cause hydrophobicity to develop, which is one of the reasons why you don't want to let that happen in the field, because it's then very difficult to re-wet it. So anyway, this seems like such a cool way to check if the wetting agents are really working. And I do have one more question about the test, though, and the way you did it. You mentioned 1 milliliter of water, and I've always done it by taking one of those cheap syringes, and like a 5 milliliter syringe or 10 milliliter syringe, and just squeezing out 1 drop of water. Where I wasn't, it wasn't like I haven't worked in a lab for long enough. I mean, it's been so long since I worked in a lab that I forget what the exact pipette is called that puts out the exact like volume of water. So I always just squeezed out 1 drop, but I never like.
Yeah, that's kind of what we're doing too. It's been like 1 bigger drop with a plastic one. So we used to use those multi-channel pipettes that have lots of little nozzles on, and you could do every other one to get your 1 centimeter spacing. Mm-hmm. So yeah, it's pretty much just a large drop of water.
And so is it exactly 1 milliliter, or it's just like?
No, it's probably a little less. It's probably less. Yeah.
But it's a large drop, the 1 gentle drop of water, and you don't drop it like rain. You
no.
You basically set the tip of the syringe on the surface and you squeeze that out.
Yep, you just kind of set it actually just above the tip, so then when it just breaks off the pipette, it just falls off there, and then that's a pretty consistent size as long as you kind of hold it just right above. You squeeze it, don't let it touch the core, and when it just falls from the pipette tip to the soil, then you start the test.
And then at the same time,
the timer.
You've got the stopwatch in your other hand.
Yep.
Yeah, so one hand
really crazy complicated.
Well, it sounds tedious.
It's something anybody can do, though, like you said.
Yeah, but it's tedious because you said it was thousands of or over 1,000 samples over a couple of years. Is that with including what was done at Wisconsin, or was that just in Nebraska?
No, that's just with us. Wow. Just with us. So if you think about it, when we were sampling every 3 spots on every green across 10 greens of different ages in different locations. And then we were doing that every, this year, we were trying to focus it right around when we thought the wetting agent was wearing off. So it was about every 3 days for 20 days after we had reapplied the wetting agent, essentially, or even before all those applications. So you start, the math starts to get pretty big. So we have just shelves and shelves of cores drying out.
That's awesome. That's impressive. I also in Australia talked with John Doyle from Simplot, and he mentioned to me that you had found that this method worked quite well, and I was like, wow, that's really cool, but it's a lot of work. And then I read your blog post and it's like, that is a lot of work. But then you end up being able to develop a model, which is so exciting. From those time measurements, you can then take those results and you can come up with a model of how when the wetting agent is wearing off, basically, and give some indication of when you may need to reapply it. Now, this was with the counter. What's the name of the product? You did this with one product, Counteract Firm.
Yeah, we needed it before we wanted to scale up. Earlier on, when we started doing this research in the greenhouse, of course, we had all these other companies that wanted to try their different products. There's a lot of them out there, and it just added to the complication when you're trying to replicate treatments and you're trying to build a method. So we just use Counteract Firm. It's one of the performance back products from Simplot. And we use their product because Simplot is, like you can imagine, this costs a lot of money, and they believed that I could do it. So they funded me for year upon year upon year to figure this method out and to build a model for them. And so that's the product we use. We use it at about 6 ounces per 1,000 square feet on the material. On the label, it goes all the way up to 8. And so we essentially just continue to apply it regularly. But every single time we applied it to all the greens, I would add check plots, little pieces of cardboard.
I'm showing a picture of that right now on the screen.
Yep.
So it's the picture from your blog post.
Yep. So we put a blue dot in the center of a plot. We put these little boards down that are about half a square foot, or in a half a square foot, or half a foot by half a foot. And then we would just go, so at the end of the year, we had, I think, 24 or 27 of these blue dots across every green that we were sampling from. And so some of those blue dots that we had to keep track of, which was also a lot of fun, they may have only got sprayed in June. And then we sampled for the rest of the summer to figure out when is the variability in those areas starting to look like the non-treated parts of a green would look. And then there's other spots that maybe were treated as recently as a month ago. And so we had different timings so that we could evaluate how fast did it stop working in the middle of the summer, when in Nebraska we're getting temperatures easily in 90 degrees, 100 degrees, lows in the upper 70s to 80, versus the spring and the fall where we're still really cold. So that we could see, can we use a growing degree day or a temperature dependent model to predict when these materials wear off. And just like good science, that concept is something we've been running through our heads back since 2016. And then Ryan Schwab at University of Minnesota did his master's degree and actually proved that wetting agent applications in the winter were lasting a lot longer than they were in the summer. So it was again giving us some idea that temperature is a big driver on the duration of these materials. And so that was kind of proof of concept. We took Ryan's work and said, let's apply a growing degree day approach to this sampling protocol, and got us to this point.
I have another question about the like that application you make in June, and then it's got a check plot on it, or the control plot that has the piece of cardboard over it, or the sheet over it, right? And then you put a blue dot there, and then when you make the next wetting agent application in July,
recover it.
You recover it, so that one spot, it gets recovered. So each time you sprayed, you had more spots that needed to be recovered, right? Because once they got covered, they never got sprayed for the rest of the season. Is that right?
Yeah, and that's how we did it in 2022, because we had no idea when these materials were going to stop working. So some of those areas were treated, and then we ran 3,000 growing degree days from the application where we continued to sample. Because we didn't know what the number was. Yep. So that's like a lot of these things, you just got to apply it once, and then you just have to get an idea. And then back in 2023, we realized the number seemed to be much shorter than that. So then we were able to just cover individual plots and then sample those out 3 to 6 weeks. And we knew that was kind of targeting the ideal window for us.
Oh, okay. So in 2022, you covered them the entire season once they entered the treatment protocol, and then in 2023, once you had an idea of when the products were wearing out, you realized that once you'd gone beyond that threshold, and it was going to be beyond the number of growing degree days that really mattered, then you would then stop recovering them. Is that right? Yeah,
like you said, it's a lot of time to be doing these water drop tests. Mm-hmm. So it didn't make sense to spend a lot of labor to sit there and put water drop tests on a plot that's at 1,000 or 2,000 growing degree days, when we know at that point, based on the prior year, that that's not the target. So we're trying to locate this point in which it's like a light switch where it's not really working and then it is working. So instead of more infrequent sampling like every 2 weeks like we did in 2022, we did much more intensive sampling right around those intervals. And so once a blue dot area that was untreated was beyond 1,000 growing degree days, we could just ignore it because we weren't going to sample it anymore. So that's how we could become a lot more efficient. So as we'll keep doing this study, we'll be able to start to figure out, ways to make it more efficient so we can scale it across more products, more rates, different soils, to see how well everything is working.
Yeah, and how there's so many questions of how it's going to work for different products and different rates and so on. Yep. I've scrolled down in your blog post to those that photo gallery of charts that starts with the one with increased water droplet penetration test variability, and then fitting a base temperature, which I don't really understand. And I'm not sure if you can explain it or not. But and then it leads up to showing that nice little probability of a counteract firm performance. So
yep.
If you want, I'll bring up maybe the first one that just shows the variability.
Yeah, and I'll talk it through with you. So on the first one, if you have that live,
that's live.
we can see that we have sampling all the way from 0 to 2,600 growing degree days. This is all in Celsius.
And
the base temperature is 0.
That's right. That's base 0.
Yep. So you can. We weren't really sure the right base temperature. If you're unfamiliar with growing degree day models, a base temperature is a point at which the temperatures get so low that the breakdown or metabolism of PGRs or wetting agents or anything, or if it's a corn plant growing, once it stops growing, how cold does it get? What's that point? And so we just set 0 right away because we don't know. And so now we're just looking at accumulating temperature on the x-axis and then that normalized water drop time. So again, normalized time, we're comparing what is the infiltration time of areas that are treated versus areas that are not treated. And so for the first 400 growing degree days, base 0, the variability is incredibly small. You can see that it's so small that those points look like they're all on top of each other. And then when we got to about 550 growing degree days, the variability starts to grow, although it's not terrible yet. And then after about 600, now the variability looks a lot more like it did before a wetting agent was applied. So you can't see this from the chart, but the high variability, that's kind of what I would normally expect the variability to look like. And so we can really see what a wetting agent looks like versus a non-wetting agent in the green versus the orange background.
I have a question about the y-axis. This is mean normalized time, seconds per second. Is that like a ratio of treated versus untreated?
Yep.
One would mean that they're the same, and then a number of 2 would mean that it was twice as much time.
Yes.
And so that allows you to account for the differences in absolute time that might have been date dependent. And so you're just comparing, like you did with the with the PGRs, the relative growth rate, basically, right?
Exactly. So we're able to, with this one chart, see 2 different metrics. We can see if we look at the around 500, if you're listening on a mower right now, you would see that the variability ranges from 1 to 3, which means the average is closer to 2. So not only is there more variability at that sampling date, But when you average them all together, it's double as long as the areas that were frequently treated with the wetting agent. So we can see more variability and a higher infiltration time. I would then say that that is not a wettable soil, or is not as wettable as it was after we just applied the counteract firm. So we're always comparing back to what would be if the wetting agent is present.
And that's in the denominator.
Yep. So it's a little different than the PGRs, in which the denominator is the non-treated and the PGR treated is on the numerator. We switch them around in this scenario because in this case we are looking at what is it relative to after when we know the product is working. So
that's exactly right. Yeah, you're treated here. Your treatments are actually untreated with wetting agent.
Exactly. So we switch it around
for a certain amount of time. Yeah. So
yep,
I got that. Okay. So I look at this and I'm like, okay, this is growing degree base 0, and it looks like it goes up to 450 or something, and it's really consistent. And then all of a sudden the efficacy starts and the variability increases and the efficacy consistency just disappears. So I'm like, okay, cool. Why don't we just make the model with a base 0? And maybe you can explain to me why you choose base 10 instead.
Yep. So what we found then, this was in 2022 and 2023, we wanted to really focus around that 300 to 800 growing degree day to figure out where is that point. Because if you notice in this chart 1, there's a lot of space between where it's working really well to where it's not. So is it 450? Is it 500? There's no way to pigeon exactly what the statistical breakpoint would be. So we needed to use a little bit of statistical method, some methods to try to figure out what the base temperature effects are and what the that kind of light switch 50 percentile point would be. So first we did the base temperature, and so we started looking for the different how long it took. And what we noticed is that in the spring, in May of 2023, we got out to 600 growing degree days, 700 growing degree days. The wetting agent was still working. But in the summer applications in 2022 and 2023, so that could be any apps in June, July, August, we made those apps, we would see that, right around 450 growing degree days. Beyond that point, we would start to see there's a lot more variability coming into the system. And so at first, we had this thought, well, it's not working in the spring, which essentially means your whole model isn't working, right? I mean, the whole idea of a growing degree day model is it works, it automatically is scaling with temperature. And so what we started to realize is if you recalculate the model with different base temperatures, you look at the point in which all of these different breakpoints start to converge together. So you do it at 0, and we noticed that in May, the breakpoint was somewhere around, in blue, 725, but in the summer of 2023, it was like 625, and it was 650 in the summer of 2022. And then you go through, you recalculate everything again with a base temperature of 2, and we see they're getting a little bit closer to each other. 24, then you 4, 6, 8, 10. At 10, now all of those breakpoints are starting to converge. And so it aligns with a number that makes a lot of sense in soil microbiology, which 10 degrees Celsius, 50 Fahrenheit, is a point in which soil microbial activity really starts to increase. So it makes sense that in May, when the soils were really cold, the wetting agents were lasting for a very long amount of time because it was below the base temperature, and microbial degradation would become significantly limited. And so that's a little bit of how you calculate a base in a growing degree day model. You have to just recalculate it and then try to refit the model to converge. So it's very science nerdy, but this is essentially how we get to that number. And it makes sense from a soil microbial population respiration perspective too.
Thank you for explaining that. It now makes more sense to me than it did before. So what those lines are showing on this summer, and then the May, summer 2022, May 2023, summer 2023, those lines are just recalculation of the break point at different base temperatures. And then how do you find that break point? Is there a statistical way, or you're just choosing that this is where it seems to break?
So the first time we did this, the way I'm showing here, was going back to our soil fertility. That's a Kate Nelson type of an analysis where you're segmenting the data into two different pools, and that's where we would calculate the break point. A better way that we're using now is we're using this segmented regression and logistic regression, which is just assigning a probability to it. And so with this, you're taking data that are very defined in their value, a time, right? And we're going to then say, we're going to set a range to say, is it in the range for what it would look like if we applied a wetting agent, or is it outside of the range? So this is, again, getting into a little bit more on the statistics of how this would work. But after we fit the base temperature of 10, if you go to the next chart, you'll notice then that there's a lot of, you can see the variability after we apply the wetting agent is averaging right around 1, so that's good. It means that the infiltration times are similar to what they would be without or with the wetting agent. And then it's ranging about 1.5 to a half of that time. So again, if the infiltration time with the wetting agent is 10 seconds, we would imagine it's somewhere between a half and 1.5, or excuse me, 5 and 15 seconds infiltration. Mm-hmm. When we got beyond 400 with base temperature 0, now the average jumped up to about 1.75 with a range of about...
I think you mean base temperature of 10.
Excuse me, base temperature 10, yep. Now we see that variability has really dramatically increased, and if we would average all those points together, we'd find that they're somewhere right around 1.75. So again, if it took 10 seconds, now it's taking 17, 18 seconds for that water to infiltrate on average, and it might be as high as nearly 30 seconds or as low as like 10 seconds in this chart.
Oh, this is great.
So we then assign a probability, a metric. If any of these points are outside of 0.5 and 1.5, or 5 and 15 seconds in our thought experiment, we'd give them a value of 0 to mean it's working. If the points are above or outside of that range, they're out of control, we give them a value of 1. Mm-hmm. Mm-hmm. And so then from that, we can do a type of regression called logistic regression. Can you just
wait a second and let me make a plea to the listeners? If you're interested in this and you are riding around on a mower listening to this, I have been really illuminated in my understanding of this. I'd read the blog post twice, and I thought that I understood what I was looking at on these charts, and I did. But now talking about it with Bill and having him explain it to me really illuminates it even further for me. So I would encourage you, if you are just listening to it, go ahead and check out the video, which I will post, and have a look maybe at these charts. I mean, if you're really interested in this, but it is really clear now what you just described as we looked at the base 10. So converting that from a base 0 to a base 10, now it's more clear where we have that average of 1. And then after about 400 growing degree days base 10, it seems to diverge. And then you've just explained that so now we're going to go into logistic regression, which confused me so much when I was taking biometry or statistics classes in graduate school. And I know it confused some other people in that class also, because it was so crazy, because the response variable is 0 or 1. And I think the confusing thing for me, and we can talk about this rather than just jumping into it, let's like talk about the confusing
Sure.
part. Because you started to describe it. You said that you say that it's working, so it gets a value of 1, which is also like 100%, right? You're just saying, okay, this is 100% it's working, and so it's a value of 1. And you do that when it was between 0.5 to 1.5. Is that correct?
Yep. And so this is again where there's a little bit, good in statistics. We just have to evaluate what does the natural variability in mean time look like right after we apply the wetting agent. So we know that's when it's working. And then we look forward to see, is there an obvious break? And there is. And so we would look at what the variability is, and we wouldn't even do it from the mean. We would do it from the value of 1. So we take a look at every single one of those dots there and say, how far away is it from the mean? That was giving us some metrics. So we had to do some statistical. We had to think about, what are we seeing here? What is our brain looking at? And it's making these connections, like these data look different than those. Then we need to figure out a mathematical model or method that can explain what we're seeing, so that we can code it into this type of regression. Essentially, if you think about logistic regression, think about flipping a coin. Heads is working, tails is not working. The 50 percentile point would be your coin. You don't know which side it's flipping. If it's a unfair coin, though, and it's always flipping heads or tails, then this type of regression would kind of show that the system, it would kind of show what you would expect at any time when you flip that coin. So if it's an unfair coin and you flip that and you expected 10% or 90% that it's going to be heads, that means 9 times out of 10 when you flip it, you're going to get a heads. A fair coin would be 50-50. An unfair coin, then on the tail side, could go to say it's going to land tails more frequently. We're using that same approach here with this model. It's similar to the Smith-Carnes dollar spot model. We've done it for predicting winter kill survival by looking at crown moisture and figuring out, is the plant dead or alive. So it's a method that we've been using, but it's essentially just assigning a probability of, is the soil have variability that's more likely to be right after the wetting agent was applied, or is the soil more likely to have a wettability similar to before the wetting agent was applied? So it's just giving us a probability. 90% probability is pretty good.
Yeah, 90% probability is pretty good. And I'm going to describe something that I see on this chart that I'm looking at right now. And the chart is showing on the horizontal axis, it's showing the final model, which is base 10, and it's going from 0 to 400 growing degree days, base 10. And so like on a hot Bangkok day or a hot summer day anywhere that's not Iceland or Scotland or England sometimes gets this hot, southern England. If your average temperature is 30 degrees Celsius, which is 80, 83 or 84, something like that Fahrenheit, then you would subtract 10 degrees, right? So that's your base 10. So basically it's 20 degrees. That's 20 growing degree days on a typical summer day. So anyway, you're adding those together. So 20, that's like 20, it's coming up to 400 growing degree days, base 10. So is that 20 hot summer days in a row, right? Something like that.
Yep. And that's what we see here in Nebraska too. We have some hot days, but more importantly, we have hot nights. Mm-hmm. In the plains. We get real hot. And so 20, 21 day interval, 3-week intervals. And it's an important point. That would get us to like a 50 percentile. So you flip in the coin. it could be working, it may not be working. You still need to kind of figure out, well, what's your comfort? Are you comfortable at maybe 80%, 60%, 90%? So there is still some dialing in, they would say, about, when you need to reapply. So you're just thinking about how much risk do you want to take in timing those applications.
So this chart with the base 10 is really good, Bill, because you've got the green shaded zone. Look at how many points are less than 1 on your, it's still in the green zone, right? So basically it's like, and I know this is tricky if you haven't done logistic regression before, or if you don't look at data on charts all the time, but this is showing that like, it's totally working. It looks like it's totally working up to that point because you get a lot of values where actually the value is less than 1 here compared to the treated. And then as soon as it shifts beyond 400 growing degree days base 10, all of a sudden there's the one single point below that 1-to-1 line, right? And that to me is really the key thing after you've explained this chart to me that shows there's clearly a break point there. It's not really working anymore at all. In fact, it's like clearly not now it's like it's so clear that the plots that have been more recently treated with wetting agent are so much better, right? That's what those numbers are showing, if I'm interpreting the chart correctly.
And exactly. And you'll see, again, it's a probability. You flip that coin, the 90%, 10% of the time it is going to come back and be, the other response. And so we'll see in this chart at about 225 growing degree days, there are 2 points with water drop penetration times that are above 2. So a lot really out of control. That shows that this is, that actually is helpful to drive this type of regression. It's all probability. You might get a core here or there that still has some hydrophobicity for who knows what, but look at how many dozens of points are within there. And again, each one of those points is made up of 3 triplicate measurement times. So it's really even 3 times these values that you're seeing. So we can get a lot of confidence that the materials are working. And then after 400 growing degree days and this for this wetting agent at this rate, we then see that there's a lot of dispersion, and in overall, the infiltration time has now gotten greater.
The infiltration time is a lot longer compared to the area of the green that has been more recently treated with wetting agent. So, it's like once you just like study this chart and study it, and I know when you're doing this type of data analysis, you did a lot of studying of this, then it's like, wow, that's very clear that wetting agents are working. And that's pretty exciting that you can get that kind of result with this very simple water droplet penetration test. So from that, you then fit the model, and I'm going to try to explain logistic regression in my way, which I haven't prepped for this. I should prep for it sometime. I have enough statistics books on the shelves behind me, but I don't make a habit of prepping for ATC double cut episodes. I just kind of wing it. So anyway, I struggled in grad school with logistic regression much more than other types of regression, because it was strange for me that you have a response variable of 0 or 1, meaning something is classified as working or not working, or it's like, it's alive or it's dead. You mentioned the winter kill one, for example. And then we're taking some type of continuous variable. In this case, in this model, you're using growing degree days. So that's a continuous variable that in this case can go from 0 up to infinity, basically. And somehow through the magic of the statistical analysis software that we use, we go from having a response variable that's either dead or alive. It's only two. It's classified into two things, 0 or 1. So in this case, it's classified as the wetting agent was working or not working at a certain growing degree day level. And all of a sudden, the output, instead of being working or not working, it's in between. It's anything but what we actually measured. It's saying that there's a probability of 1% that it's working, or there's a probability of 99% that it's working. And when you first get introduced to that type of statistical procedure, maybe for people that are better at mathematics than I am, or people that their mind maybe their mind works differently and they instantly understand it. But for me, it took a long time. But now I'm like, wow, this is so useful, because we don't really care about the 0 and the 1. What we care about is exactly what you've modeled, which is the probability that it's working, because from that you can make a decision. And I think that's part of the reason why the Smith-Kearns dollar spot model is so popular, is because there's a range of probabilities, and if you're close to 0, then the dollar spot is unlikely to be causing an epidemic of disease, and if it's close to 100%, then you probably have dollar spot. So I've brought up the next chart, which is a ggplot2 output with that characteristic gray background, and I see that you've got your probability of counteract firm performance.
Yep. So again, this is at 6 ounces per 1,000 square feet on a sandy push-up style green. So essentially a value of 0, because of how you do logistic regression, it has to have this shape. So we had to say it's working was a 0, not working or out of control was a 1. And then we just follow along, and it tells us from a probability of it being either working or not working. So if we just follow along here at, say, 300 growing degree days base 10, we see our probability of it working is around 95%, or 5% that it's not working.
Right. So
at
the
400 growing degree days.
Yeah, the y-axis could be reversed there. So just think of it, if it's low there, then if it's around 0.05, that would be, which it's not marked on the graph. So like 0.25 would be 75% chance that it's working, 25% chance that it's not.
Exactly. We had to switch it just to make the stat software happy, because it wants to do this shape of a curve. Mm-hmm. And so there's our 25%. So that would be at about 450 growing degree days. Now there's only a 75% chance that it's working. And then when we do this type of analysis, a lot of times you use the 50 percentile as your breakpoint. So then you can evaluate at that point, which in this case was to be about 500 growing degree days for this one. That would be a breakpoint where it's likely to be working or not working. And this comes to a really important point. It doesn't mean there's a 50% chance that the soil is now completely hydrophobic, and if it dried out, it would be dead. It's not what it means. It just means that the wettability of the soil is what it was before you applied the wetting agent, right? So it just means that it doesn't mean that everything is now not accepting water. It just means the variability returned to what it was before the wetting agent was applied. So that's an important thing to remember.
Which that happens to be exactly at 500, that 50% point. But
yeah, and this was actually, I didn't have the chart available for the 6 ounce rate that I used. This was what Doug Soldat's data showed, and this was at an 8 ounce rate, so a higher number. And we see that by going at more product, the interval, or that 50 percentile point, moves slightly to the right from 450 to 500. And so these are some of the questions we have left are, what does rate do? How do we evaluate different wetting agents with this type of an approach? There's a lot of work we have to do still, but at least we have developed a model to start to do those evaluations and analyses.
That's really cool. So I've switched to just showing me, you, and a background image of a cup cutter plug from India from a hydrophobic green, and demonstrating the water droplet penetration test in real life in New Delhi, I think many years ago. So this is so cool that so we've talked for like an hour about what you did and then all the statistics and stuff, and we haven't quite gotten to the part about like how why am I so excited about this that I wanted to talk about it right away? Why did you go to the effort to write a 1,400 or 1,700 word blog post or whatever about it? Why is this exciting? Why is it added to Greenkeeper? What can people do with this type of model?
Yeah, so one of the things I did first is I went back, and once we had this predictive model coded in the Greenkeeper, and kudos to my development team, we have 3 really talented computer science guys on staff. They were able to build this in about 5 days for me, and thanks to Michael Carlson, our research manager, for helping to do all the regression and data analysis. Essentially, then I was able to go back in time and figure out how well did I time my wetting agent apps when I was just following monthly intervals from April 1st all the way through November 1st. And what I quickly figured out was that I was over applying wetting agents in the spring because an application in April wouldn't wear off until late May, early June in Nebraska. Then the June application would generally be pretty good, maybe around that 4-week interval. But July and August, I needed to be applying every 2 or 3 weeks because the temperatures were high. And so this is exactly when water management is most important and crucial. And I am now not applying it as frequently as I should. And sure enough, when I was having issues, when I was really chasing dry spots with a hose, then that's when I look back at this chart saying, oh yeah, I only had a 35 or 40% chance of the wetting agent even having an effect at that point. I needed to apply much earlier. And so what I'm getting the feeling is I don't want to stretch my intervals longer than a 75% chance that wetting agent is working. I think that's a good conservative number. It's not going to waste wetting agent by applying more frequently than that. But it's not going to get me into an area where the chances of it working aren't there, and I'm spending a lot of time with a hose chasing dry spots from forming. So I really realized that it went from weeks to 6 to 8 week intervals back down to 3-week intervals, and then if I made an application in late September, I was good all the way through until next March or April, with the cool weather and the base temperature of 10 Celsius. So completely same number of applications, just schedule them differently to try to have a better likelihood of success.
Very good. So you think it makes sense for 75% chance that it's working, which that makes sense after you've explained it. Yeah, because like you don't want to go all the way to where the efficacy is completely worn off, and that's at the 50% point. And you described it's not necessarily that means that you have terrible hydrophobic conditions. It just means that you're at the point where it's the same as if you hadn't applied wetting agent. It's the same as it was before. But when you apply a wetting agent or a soil surfactant, you typically want it to have an effect. So you don't want it to run out. Like it would be like if you're on a preventative fungicide program, for example, and then you go way beyond the time in which the product is actually having an effect.
Yeah, think about the fungicides. I mean, most of them have a reapplication interval of 14 to 28 days, pretty standard label. You'll know during high disease conditions, the label might say that you have the potential probability that maybe it will get 28 days. But then from your experience, you go, no, that I need to be a little bit more conservative. I'm going to err closer to the 2-week interval. It's that same kind of a thought concept. So if you have sands, for example, that are maybe there's not much hydrophobicity there, newer greens, or if you're on a light and frequent daily irrigation, like deficit irrigating, you can probably stretch it closer to that 50 percentile point, because those sands are really pretty receptive to water. And by watering every single night, they're not drying out as much. But if you are going to more of a deep and frequent scenario where you're doing a lot of water, you want to make sure that that water gets in everywhere and infiltrates uniformly through that soil for your next dry down period. So that superintendent might want to be at a 90 or 80% risk, because they want to make sure when they do put that water down that it is going to get into that soil. And so that is where the end user can start to make those calls, because applying more frequently is a lot more money. And we're also curious of what it could mean for playability, performance, firmness, some of those other secondary attributes by over applying your surfactant, versus the trade-off of going too long, saving the money, but then maybe having to overwater to try to re-wet things after a dry down cycle.
What about different products? So this is for the counteract product.
Yes. So there's going to be a lot of variability in there. We have done a little bit of initial work with some of the older chemistries, the more linear chemistries. So their shape is just more of a line of molecule. Some of our introductory or preliminary data shows that those materials, the counteract, you see a really big spike when we see the wetting agent stop working. Some of the older chemistries, it's a lot more flat. So if you put down the wetting agent and you start at 100% probability of it working, it's going to kind of slowly decline over time. And so I think there's going to be a lot of shape of the molecule is going to be really important. I know some of these newer molecules have different branches or arms that are kind of like a Medusa head, I imagine. You know, we have the center part of a molecule, and then it has these different arms coming off that interact with the water and the soil. And I think that those materials might be longer lasting than maybe a straight linear material that a microbe might be able to more quickly degrade. And then soil conditions are going to be important too. And so that's going to affect potentially the shape of these probability curves. And then the other factor is, what if we use a 4-ounce rate, a 6-ounce rate, an 8-ounce rate, a 10-ounce rate of these materials to get an idea how to compare them. So right now, these probability curves, they only say, is the wetting agent working or not working relative to the rate that you used at day 0. So we have to find out ways to compare different rates and intervals. I'm assuming it's going to look a lot like the PGRs, where the rate impacts the amount of response you get out of that material, and temperature is what's going to really dictate how long it lasts. And by, say, doubling rate, you might get a couple more days of control out of it, but I'm not imagining you're going to get double the amount of control out of the material. So lots of research. Another thing too is it makes sense to do a lot of loading of wetting agent early in the spring, even though the breakdown rates are slow, just to really make sure that that soil is thoroughly treated with the material. And then you just make maintenance applications at lower rates through the summer. Is there, we know that that's a common practice. It'd be great to try to apply these types of models and evaluate how effective they are. So I just see a decade of research ahead of me in this space.
Yeah, potentially. And, with all the products on the market, you'd think that people might like to have you do testing on their products to demonstrate how well they work. So it
Exactly. So we'll see how the next few years go as we start to dive into that and evaluating these products. Ultimately, I think we can maybe even start to group some of these products together, just maybe not in molecular structure, but on the type of probability shapes that we see. and then being able to compare one versus another too. So I'm pretty excited. I feel like in your career as a scientist, right, you have a couple of big things, and my first part was the wetting agents, always the PGRs. I'd like to think that some of the things we're doing with the spatial, with GPS sprayers and the sensors on mowers, I hope that has a big benefit to the industry. But I'm really excited about this wetting agent, just like I was the first time we built the first PGR model, and thought, wow, there's a lot that we can do with this type of research. So I'm pretty reinvigorated to dive into the.
It is pretty exciting,
studies.
And by doing this kind of research, it's not like the typical like just product efficacy work, and then you're rating the quality on a scale of 1 to 9, and then at the end of the year you have a summary report. But this is like more making a model about how it's working that can be transferred to a lot of places. And I think from this, as you hinted at earlier, you said maybe you can figure out that loading up with frequent applications early in the season can make sure that all the soil particles get coated and that you really have good efficacy going in. And then all the future applications through the year might work even better. And like you can get those kind of ideas and then test it pretty quickly, I think, with this type of research, the way that you're doing it. So I think not only does it make these models, but it can lead to some insights into overall better use of a more effective use of soil surfactants. So that's cool. I had this question I meant to ask earlier. I know Doug in his 2010 paper, I think, used soil something to check variability that was probably a soil moisture meter. You must have tried soil moisture meter, because that's easier than pulling cores, letting them dry for 2 weeks, and then timing them with 1 milliliter drops of water. Did you try that, and does it work, or does it just not give the type of precision that you need for this?
It doesn't give the precision, especially in our scenario where we had putting greens that are real world. So we have slopes, low areas, different conditions, traffic, walk on, walk off locations. Back in 2022, this is actually kind of interesting. It's not in the blog article, but of those 10 greens that year, we actually segmented them into 3 different irrigation profiles. We had nightly deficit irrigation. We had deep and infrequent, and then we had more of a model-based irrigation where we'd only apply as we approached our wilt points, and then we try to predict what we need the next day. And when we look at those irrigation strategies, we still see that these models are working despite different irrigation programs. So this is kind of an interesting aside you might like. But yeah, the moisture meter, then we were going out and taking literally hundreds of readings across putting greens, and you just get a variability number, but it's a lot. It's hard to really use it to figure out if a wetting agent is working here or there. And so I think it's a good secondary metric, especially evaluating wetting agents and maybe a flat research green. But when you're trying to determine when a product isn't working anymore, then I think it isn't as helpful. So I think maybe in evaluating those rate effects, like we talked about before, it could be useful for that, to see maybe higher rates change. And we've done that in a fairway study on a native soil. We looked at Rely 3 wetting agent from Simplot at 4 different rates, and we found out that the highest rate of wetting agent had less uniform, less variability, and actually had lower levels of water content. So there was a rate response there. But I think it's just one of the tools in the toolbox that we need to really evaluate how these materials are functioning.
Cool. Where can people hear from you this winter? Are you speaking at some upcoming conferences, or are you going somewhere in the summer?
Couple. No, I've definitely been traveling a little bit more though. My schedule for this winter isn't as packed as past years, which is fine. Which is good. I'm going to speak to the metropolitan superintendents in New York City, at Westchester the second week of January. Then I think the following week I'll be at the We1 meeting in Chicago area. I'll have a couple of different training things with Simplot in Portland and Seattle. So I'll be around a little bit, and trying to also be at the Canadian National Show too. So those are some of the ones that I definitely have in my schedule, and that's starting to fill up. Otherwise, you can see all this information on our greenkeeperapp.com website under the blog. And I really appreciate everyone following me on social media so that I can get out this information. And if you're interested in our newsletter too, then signing up for a Greenkeeper app account, which is free, you'll be on our listserv, and then you'll get all of our newsletters, which I would like to be more than monthly, and I'll try harder to do that in 2024. New Year's resolution.
You know, if you've got that 9,000 subscribers or 9,000 email addresses, maybe I will ask you to send out a few suggestions to people to sign up to mine so I can get more than 1,000. Because I also share interesting information that's a little bit more frequent than you do. Well, I'm glad to know that you'll be at the Canadian National Conference, because I will also. I'll go ahead and say what I'm doing. So I'll be in Hong Kong at the South China Turf Managers Association meeting at Clearwater Bay. I believe that's January 19th. And then I'll be in Tokyo for a couple of private seminars, February 19th. And then I'm going to be in Montreal at the Canadian National Show, where I'll see you and we can catch up in person, which is going to be awesome. I haven't seen you maybe since Thailand. When was the last?
It's been a while. No, maybe. It might have been Thailand. That's a long time. That's a problem.
It has to be, because I don't think I've seen you in the U.S. since then. So yeah, but
no, I think the last time I saw you was at the crop science meeting. No, it was that we played golf.
Oh, yeah.
That's when I saw it. Remember when we played Sand Valley with Soldat and Kearns and Coke? That was the last time we saw each other.
You were my photographer.
Yeah.
I made those amazing.
You had the birdie.
I made 2 birdies. And I'm just going to make a note here that I can share a link to that blog post also with those birdie dances. Yeah. So that was that
was a fun day of limited turf talk. It was a good time.
Yeah, we talked about sand a lot.
I think it was June of 2019.
It was end of June, at like June 30th, 2019, something like that. Yeah. That was awesome. So yeah, that 4 years ago, 4.5 years ago. Right. So we'll see each other at the Canadian National Show. So for anybody that wants to go to a great conference in a great city, I'm sure there's a lot of other good speakers also, but Bill and I will be teaching on various topics there. And then the Thai conference is back on, and Michael Becken and Devin Carroll will be speaking. So and Bruce Williams giving a very popular talk about what it takes to be a successful golf course superintendent. And so that conference is on. That's going to be March 4 to 6 in Pattaya, Thailand. It's already been approved for Australia Sports Turf Managers Association continuing professional development points. And it's quite a nice conference in a wonderful beach resort town. Bill spoke there 2017 or 2018, I think.
Yep.
And then, I think that's what's on my schedule for now. So, everybody check out, I'll put links in the show notes, video description, whatever. I'll put links to all these blog posts and to the Greenkeeper app. And I just want to say, if you've listened this long, there's a reason why I wanted to talk with Bill right away. I think he and I both agree. I mean, he's rightly excited about it, that this is kind of a potentially groundbreaking thing. I mean, it's a product that everybody uses, or I mean, if you want to get the best turf on a sand-based root zone and you want to apply water effectively, and use a minimal amount of water while still having good turfgrass quality, high quality turfgrass, you almost have to use some type of soil surfactant. And so to have a model like this, when you can predict whether it's working or not, and to really time those applications at any time of year, potentially anywhere in the world, so in Reykjavik, you'd have a certain type of reapplication schedule. In Montreal, you'd have a different type of reapplication schedule. In Bangkok, you'd have a different type of reapplication schedule. That's something that's really, really cool. So, I was so excited about it, and I just love that logistic regression approach. So,
as long as we didn't lose everybody on the mower during that section of the show today, but yeah. It's a little bit.
We'll find out.
I have in the blog. It says a science nerd alert. I think because I know that people will be like, "Whoop," because that was me in that class too. So, yeah.
Well, it's good. I think it's fun to try to talk through it in detail. Because again, I mean, if somebody's tuning into a podcast with Bill Kreuser and Micah Woods, they probably want to kind of know some details about turfgrass. So I think we're happy to provide those details. But actually, like for the end user, it's really practical. Is you just and the Greenkeeper app has that programmed in where you can just say, okay, I've applied the product on X date, and it's going to take your site weather, and then it's going to say, okay, you're now 12 days into it, and this many growing degree days have accumulated, and now your probability, based on this model, the probability of the product having its full effect is 67% or something like that.
Exactly. It's supposed to be simple. You have to do the math anyways to figure out how much product you're putting in the sprayer tank. You just say, I want to use this rate, and then it sees it and it starts tracking it because it knows that that's counteract firm. And again, as we add more wetting agents, you'll just select the wetting agent that you use. And for now, even if you don't use counteract firm, just try it. Put it in your inventory, throw it out there, do it on your plan for 2024. It'll use the weather normals to make those predictions and just get an idea of, how different is it from month to month across your growing season. So, have some fun with it. 7-day free trial, sign up, make a course, schedule some PGRs and some wetting agent apps and get an idea if you needed to tweak your program for the next year.
Very cool. Well, I think it's great timing for you to release this also, because for everybody in the Northern Hemisphere, they've got a few months to kind of plan how they're going to be doing this. And I guess we do have a lot of people in the Southern Hemisphere who pay attention to this too. So they're kind of coming right into their summer. So maybe they already get some hints that they can start applying this right now, and maybe shorten up those intervals if they do have some pretty high growing degree days. So anyway, I think we talked about this long enough, Bill. Thank you so much. And again, everybody will be able to check out in the links. There'll be some interesting stuff there. Anything else before we go?
No, just last thing, if you are going to the GCSAA conference and trade show, we'll be there. I'll be at the Simplot booth again, since they're helping to promote and sell our product. So if you want to talk about this, see sensors on mowers or see our new CIS software, please stop by that booth and say hello. And I look forward to seeing you, Micah, later this year too. And thanks for the opportunity to talk about our exciting new research.
Yeah, my pleasure. All right, everyone. I'll sign off now. Thanks for watching, listening. Thanks, Bill, for joining. For ATC from Trong, Thailand, I'm Micah Woods. Bye-bye.